So welcome back. So far in this course we have used discrete distributions. And discrete distributions, they are great for us to gain intuition. So we can look at the tables, we can multiply them, we can marginalize the variables, and we look at the tables, we see the results, and also we can count the number of parameters and estimate the complexities and so on. So discrete distributions are really great for us to understand the underlying ideas that are in the probabilistic graphical models. But not always we can well represent a variable using discrete distributions. So far we have made some very naive approximations. So when we talk about temperature, we say something like temperature hot and cold. But of course, this is not a good approximation. We can often using discretization to represent the variables, and sometimes that's a good solution, but in other cases we want to use the continuous variables. So we're going to see that using continuous variables is a little bit more complicated than using the discrete ones. But when we define the operations of multiplication of the factors and marginalization of the factors, we can easily adapt everything that we learned with discrete variables to this continuous space. So in this lecture, we're going to talk about Gaussian models. So we're going to use Gaussian distributions, and we're going to see that using these Gaussian or normal distributions is very easy because we can easily define the operations of factor multiplication, factor marginalization, and also setting evidence into the factors. So we're going to see how we can implement Gaussian Bayesian network, and we're going to see how we can operate over this network. In the end of the lecture, we're going to talk about Kalman filters. That's basically a hidden Markov model into the continuous space. And we're going to see that we can use everything that we learned and the operations that we defined to make inference over those models. So let's take a look in the next slide. All right, so in this lecture, we are interested in continuous variables and models that use those variables directly. So we're going to focus in the Gaussian distribution, right? And we're going to see that the Gaussian distributions are interesting because we can find a representation for those Gaussian distributions that we call the canonical form, and we can easily implement the operations that we need in order to make inference over those graphical models. We're going to apply these ideas to a Bayesian network, and we call this Bayesian network the Gaussian Bayesian network. All right, these ideas can also be extended, and we can easily do that for different types of networks, including the undirected models like the Markov networks. We're going to see that everything that we learned about probability calculus is still valid for continuous distributions. So ideas like independence, conditional independence, the Bayesian conditioning, the product rule, the chain rule, the case analysis. The case analysis changed a little bit because we send out a variable and now we need to integrate that factor in order to remove the variable. But the idea continues to be the same. It's just the operation that changed from discrete to a continuous distribution. But also the base rule is the same and so on. And the main technical development of this lecture is the representation of the Gaussian factors into a canonical form. So we call it the canonical form. You're going to see that is a representation for the Gaussian factors that allow us to make the implementation of the operations in a simpler way. So we're going to implement operations like join, marginalization, and reduction. That is basically the observation of evidence using those canonical forms. And it's going to be interesting to see that when we join two factors represented in the canonical form, we get another factor also represented in canonical form. The same thing happens for marginalization and also for reduction. So we can easily work with this, and we're going to also see how we can transform a Gaussian distribution, can be unidimensional, multidimensional, or even a conditional Gaussian distribution into these canonical forms. And we're going to conclude this lecture talking about Kalman filters. And we're going to see that Kalman filters are very similar to hidden Markov models that we haven't seen before, but now using those Gaussian distributions. Okay, so our challenge is how to incorporate those continuous variables into our models. And of course, some quantities are better expressed into the continuous space, and we can think about something like temperature or humidity or a position and velocity of a robot. And if you think about temperature, what we have done so far is a very coarse approximation. We have simplified and said, okay, we're going to look at work with a binary representation, and temperature is hot and cold. Of course, we don't need to do that. We can do much better. And one standard technique for doing that is to discretize the variable. So we do an operation that is illustrated in this figure here. That's basically we split the continuous variables into bins, so into smaller ranges. And if we use for some variables something around 10 bins or 20 bins, we get a quite reasonable approximation of the continuous function. So if we do that, what we win is the fact that we can still use the tables, right? So we still represent these different values for the bins into a table, and we associate that to the probabilities, and we continue operating with the techniques that we had so far. However, the problem with discretization is that it doesn't scale up very well when we have large search spaces. So we can think about the problem of a robot localization. So we have this small robot here. We want to find where it is located in the map. And if we try to discretize the space of the map, we need to come with a very thin grid where each cell here is going to approximate a small portion of the map, right? However, if you want to be precise, we will need to have something like the cells are 15, for instance, centimeters by 15 centimeters. So now imagine we have a large map split into a small, very fine grid of each cell having 15 by 15 centimeters. You're going to probably have a very large number of cells. So those tables are going to be huge. And making inference over those tables will be very inefficient. So discretization is not a good technique to solve this, and probably we're going to be better if we represent the variables into the continuous space. And another thing that we lose when we change from continuous to discrete is the fact that we don't have in a very clear way the idea of distance that we have in a continuous space. So for instance, in this grid here, we can think that we have cells, and we're going to say that is a row A, B, C, D. We have columns 1, 2, 3, 4, 5, and so on. And we can talk about the cell A1 and the cell B2 and so forth. But however, it's a little bit tricky to come with the idea of distance when we are talking about those cells. It's a lot more natural when we have the continuous variables that we can calculate something as simple as, for instance, Euclidean distance between 2 points. So summarizing, for some quantities, for some variables, it's much better to represent them in the continuous space than trying to discretize those variables and work with them in the discrete space. And we have worked a lot with discrete variables so far, and it was important to gain intuition into the underlying ideas of probability calculus and probabilistic graphical models. But what do we lose when we change from the discrete into continuous space? Something that we don't lose at all is many of the concepts about probability calculus that we haven't seen so far. So ideas like independence and conditional independence, they continue to be the same. So for instance, it is still true for continuous variables that the variables a, b, if the variables a, b are independent, then we can compute the joint probability of a, b as a multiplication of p of a times p of b. So we don't lose those ideas, and the same thing applies to conditional independence. We also don't lose all the equations that we learned about probabilities, and those equations these are always true. They are true for discrete and continuous. They do not assume anything particular about any distribution. So if we talk about the continuous distributions, they're going to be true for any of the continuous distributions, the normal distributions and all the other distributions that we have. And they also do not assume anything about independence. So we know, for instance, the base conditioning, right, continues to be true, the product rule, the chain rule, and the Bayes rule. And we also have this idea of case analysis that we use for doing marginalization. It continues to be true. The only thing is that as we switch from the discrete space into the continuous space, we're going to change the operation of summation by an integration. So the idea is still the same. And what do we lose? Something that unfortunately we're going to lose is the use of tables to represent the probability distributions. And I say unfortunately because those tables are very interesting for the discrete distributions because they are universal representations for different probability distributions. So we didn't care about what was the probability distribution. We were using the tables as far as the variable was discrete. Unfortunately, we cannot do that anymore because if we have a continuous variables, we can understand that the table is not a good representation for that. And we're going to switch from tables into probability density functions, or PDFs for short. And the idea of using those probability density functions is that we're going to switch the table into a function, and we need to operate over those functions. So now when we talk about multiplying two probability distributions, before we were talking about multiplying two tables, now we're going to multiply two functions. So we can expect that those operations were going to be a little bit more intricate in order to implement. As we're going to work with Gaussians, we're going to see that we can use a canonical representation, and this representation will simplify a lot the implementation of the operations that we use for inference. And we can see here in this plot the shape of the Gaussian distribution that I assume that you are already very familiar with. So the Gaussian distribution has two parameters. One is the mean mu, and the other one is the variance sigma square. And the variance controls how wide is the distribution. So we can see here that the blue, the red, and the orange distributions here have the same mean, 0, and different variances. So we can see how much wider is the orange distribution compared with the blue distribution. And we can also shift the distribution to the left or to the right by changing the mu. So we can see that the green one is shifted to the left because it has a mean of -2 compared with the other ones that have mean 0. So in this lecture, we're going to work with Gaussian Bayesian networks. It's basically the idea of having Bayesian networks with Gaussian factors. So I think that we can illustrate the idea of Gaussian Bayesian networks with one example. So imagine that we have a building and we want to measure the inside temperature and we want to control that. And we want to know how much energy we are spending by heating or cooling the building. So in this very simple example, we have the inside temperature that we are calling I, and also the outside temperature that we are calling O. And we can think that we can model those variables using Gaussians. And Gaussian distributions are very popular because we can model different real phenomena using these distributions. So we can think about the temperature, right? So the temperature, we can think that if we think about the number of days that had a certain temperature, we can think that most of the days have temperatures that are close to the average here, the mean. And we can expect that very cold or very hot days are relatively rare. So the probability of having a very cold day or a very hot day, as we go away from the mean, it decreases. And in the case of the Gaussian distribution, there is this exponential decrease as we move away from the mean. And in the case of this problem, we have the inside temperature and the outside temperature. And we can think that we can model the inside temperature using a certain mean that we are calling here the mi, and a certain standard deviation that we are calling sigma I square. And we can think that the outside temperature will have its own mean, so it's going to be MO, and also its own standard deviation or variance. In this case here, the variance is sigma O square. And we can think that because we have inside temperature that they are controlled, maybe the variance of the inside temperature is going to be smaller than the variance of the outside temperature, right? So this is an assumption. Actually, we can get that information maybe from data. If we have data about the temperatures in different days, inside and outside, we can compute that mean and standard deviation from data, and you can use that to model the problem. All right, so for this problem here, the root nodes are simple to model. We can use univariated Gaussian distributions, but now we need to model the internal nodes of the Bayesian network. So in this case, we have the sensor S and the energy E. So how we can do that? So a simple solution is to use what we call a linear Gaussian model. So what we're going to do is basically think how we can define a conditional probability distribution that we call the CPD. Remind that before we have the conditional probability tables, right? So T is for tables. And now we talk about the conditional probability distributions. So D is for the distribution. And we need to define these conditional Gaussians. How we could do that, right? The idea of this linear Gaussian model is very simple. What we do is to define the mean of the internal nodes as linear combinations of the parents. So let's think about the sensor. What would be the mean for the sensor? Let's suppose that this sensor is not biased. So the mean should be the same as the inside temperature, right? Or the variable I. So I define here the mean of this conditional probability distribution as the parent I. As the inside temperature changes, we see that our conditional probability distribution for the variable S also changes. And in this case, we need also to define a variance. And for the linear Gaussian model, this variance is independent from the parent. So this is a simplification. And you can, for instance, look at the technical documentation of the sensor and see what is the error expected for different measurements, and we can define what's going to be this standard, this variance sigma S square. And we can also think about the energy, how much energy we're going to consume. And let's think that in this simple model, this energy consumption depends on the inside temperature and the outside temperature. So we can think about if the outside temperature is too cold compared with what we want for the inside temperature, we have to spend a lot in heating. If the outside temperature is too hot compared with what we want for the inside temperature, we can think that we need to activate the air conditioning and cooling the inside the environment. So what we can think is that we can define the linear combination. So we're going to be a certain factor beta 1 that's going to be multiplied by the variable I and summed with another constant here, beta 2, that's going to be multiplied by the outside temperature. And if you have, we can also, if you want, we can also have a bias term here, beta 0. And again, this will be the mean of the Gaussian, the conditional Gaussian for the variable E. And we can also define its own variance that will be independent from the parent. And that is basically the Gaussian Bayesian network. So this idea that we have in the root nodes we have univariate Gaussian distributions, and for the internal nodes, we have the linear Gaussian models. Is what is the central idea of the Gaussian Bayesian networks. I think that this is a model that's interesting because it's very easy to understand. Because we have these univariate Gaussians, it's very simple to plot these and visualize these ideas. And the conditional probabilities that are a little bit more complicated, they are still a sort of a univariate Gaussians, because we have just a mean that is a linear combination of the parents, and we define a Gaussian over that. So it's very easy to explain this even for non-experts. So let's define this linear Gaussian model a little bit more formally. So what we have an variable x that is an internal node in a Bayesian network, and we have the parents u1 to uk. And we defined the conditional probability, the probability of x given the parent, as being a normal or Gaussian distribution. So we use this symbol here, this special n, to indicate that is a Gaussian distribution, and it has two parameters. The first one is a linear combination of the values of the parents. So we need to define those constants beta 0, beta 1, and 2, beta k, that are going to multiply by the value of the parents. So this term here is usually special. We call this bias, and sometimes we use the symbol b as well. Also we have a standard deviation or a variance that is independent from the parent, so it's going to be a constant here. And we can make the same definition, but now using the vector notation. So it's going to be probability of x given u. Look at that, we are using u in boldface, so now u is going to be a vector. It's going to be a normal distribution, bias term summed by the multiplication of two vectors. Is a beta transpose times u. So what's the idea here is that this beta transpose times u, we're going to replace all these sums here. So we're going to have the beta vector, there's going to be a column vector that will have beta 1, beta 2, until beta k. And we also have another column vector that is u, and u has the instantiation of the parents, u1, u2, until uk, right? And we're going to make the multiplication of this. So in order to make the multiplication, I need to transform the beta column vector into row vector. So I'm going to compute the transpose. So it's going to be the multiplication of beta 1, beta 2, into beta k times this column vector u1, u2, uk, right? And when we make this multiplication, what we're going to get is beta 1 times u1, so it's going to be beta 1 u1 plus beta 2 u2, beta 2 u2 plus, and we keep on doing that, and we multiply beta k uk, right? Exactly what we have here in this part. And we need to sum with the bias component here, that is beta 0, in order to have the whole equation. We can also think that the x is a linear function of the parents u1 to uk with a Gaussian noise of a mean 0 and variance sigma square. So in this case, we can think that x is going to be the result of a linear function that is all the constants beta 1, beta 2, and 2 beta k multiplying the instantiation of the parent plus a bias term. And we now introduce this epsilon here that is basically introducing the uncertainty into this equation. So epsilon will be normal distribution or Gaussian distribution. It's going to be the noise term with mean 0, because if it doesn't have mean 0, it will influence and change our bias term. So we're going to have mean 0 and standard and the variance sigma square. So finally, a last observation here, and we haven't talked about these before, but when we're looking at this term here, the variance, we see that it's not a linear combination of the values of the parents, it's a constant value, right? And this is a simplification that we have in the linear Gaussian model. Of course, we can change that. We can think about the situations where we want to increase uncertainty as we change the values of the parents. So we can think about the sensor that may have a larger error when we have higher temperature. So we want to increase the variance when we increase the internal temperature. But what we often do is to keep this as is a constant value. It tends to be a very good approximation to many real situations. So people like the model as it is. Of course, we can extend that, but something that we like about the Gaussian models, and we're going to discuss that in a few slides, is that there is a simple mapping between the linear Gaussian models and the multivariate Gaussian distribution. So we can easily convert a linear Gaussian model into a multivariate Gaussian distribution and back from the multivariate Gaussian distribution into a linear Gaussian model. So it's also one of the reasons that make the linear Gaussian model so popular. Alright, I think that's good for this video. Let's take a break and continue the next one talking about the Gaussian distribution. See you soon.